Okay, so as you guys may have figured out by now, or gotten an impression for it at least, classical mechanics is what we've been doing this whole semester, or for the majority of it at least, which is, I'll abbreviate as CM for the rest of this talk. It is deterministic and symmetric in time. So what do those mean specifically? Deterministic means if you're given all the initial conditions and everything that's going on at one point in time, you can predict what's going to happen at any point in the future or the past for that matter. So typically what we would do is we work out all the forces acting on a system, sum up all the forces, set that equal to the masses times the accelerations. And if we know all the initial positions and all the forces acting, then we can work out the equations of motion and determine what happens. So it's completely clockwork. If you know what goes into the system, if you know what's going on at one point, you can predict what happens for all points in the future. Also, if you flip the direction of time, if you send t to negative t, nothing really changes. If you look at a ball flying through the air, and then you just run the clock backwards, you'll see a ball flying backwards through the air. And that's just as good of a motion as it moving forwards, right? We know that things happen to fall down, but if they fell up, you wouldn't really know if maybe, you just turned the camera upside down. So if you imagine running a movie backwards, if everything that's going on is being described by classical mechanics, you can't really tell which direction time goes. This is in stark contrast to what we actually observe in reality. You don't get younger as time goes on, and you don't crawl back into your mother's womb when you get old, right? If you drop a coffee cup, it's going to break, spill coffee everywhere. You can leave that coffee cup on the ground all you want, and it's not going to spontaneously form back into a solid cup and jump up off of the ground and hop back into your hands, right? That never happens. Time is decidedly asymmetric. And one really important point I want to emphasize about this is that this means this is a serious shortcoming in classical mechanics, right? The job of a physicist is to come up with a model that describes reality, that we can use to predict what's going to happen and describe and model how things work. The universe is not symmetric in time. Our theory is. So that's a problem with the theory, not a problem with the universe. Does that make sense? So kind of keep that in mind. That'll be sort of a theme for later in this talk. Quantum mechanics, which we haven't gotten into, but some of you guys may have read in some popular science books that when you get to really small things, really cold things, there's a new set of physical law that takes over, and it's called quantum mechanics. And in this case, quantum mechanics is not deterministic. That's the main distinction between it and classical mechanics. But more importantly for the purposes of this lecture, but it is still symmetric in time. When you describe a problem using quantum mechanics, you have these things called wave functions that you use to model what's going on, and they evolve in time. And this evolution of wave functions is entirely time symmetric. There's a thing called the collapse of the wave function that happens when you observe it. When you observe some quantum particle, it changes its states. You guys probably heard of Schrödinger's cat and that type of thing. And that is not symmetric, but that is not an analytic component of the theory. That is something that we've observed happens, but we don't actually have a description for it. So as far as how quantum mechanics works, it goes equally well forward and backwards. So as I mentioned, nature is not symmetric. And what we're going to do today is try to investigate where this discrepancy comes from. Okay, so the main reasoning is that time symmetry in classical mechanics and quantum mechanics is more reflective of how we like to think about the world. And how we like to conceptualize things. Than it is of how they really are. So what do I mean by that? So when we describe things, we like to put everything into nice, neat little boxes where you have things at certain positions and they're going in certain directions and everything works out. And then when you have something that's so neat and tidy, then of course it can run in either direction. The problem with reality is that it's not neat and tidy, it's a big mess. And so there's a number of assumptions we implicitly make in classical mechanics that are just not validated. They're not fair assumptions to make. And they are as follows. There's three limitations, three main ones, on classical mechanics, on our models. One is we can't know the initial conditions of some situation exactly. Right? Exact means infinitely precise. You can't say where this pen is to within an infinite precision. Right? There's no way to do that. You don't have anything that you can use to measure something with infinite precision. Whenever we're talking about classical mechanics, projectile motion, you say, okay, it was at x equals 3 meters. It had initial velocity of whatever, 2 meters per second x hat plus 3 meters per second y hat. Those are all not just, it's not just 3 meters per second. That's actually 3.0 with an infinite number of zeros afterwards. It's an infinitely precise point in mathematical space. That is the first way that classical mechanics sort of breaks its connection to reality, that there is no way of, first of all, justifying that velocity is that precise, and second of all, it just won't be, because you can't observe or in any way measure an infinitely precise quantity. So that's the first limitation. A second one is that the universe is not composed of point particles. Right? When we're doing these things, once you break into the center mass of something, you say it's just a point particle that's moving somewhere. It's a super useful way to approximate things, but it's not exactly accurate. Everything has structure. If you look into, if you approximate the nucleus of an atom as a point particle, it actually has protons and neutrons, which are themselves composed of quarks and things like that. There's no reason for the universe to suddenly become this nice little Lego set that we want it to be when things get really small. Even as much as you would like the universe to become super simple and tractable when you get to ultra microscopic levels, there's no reason for that to be the case, and it's not. And it's one really interesting thing about, it really gets into ontological questions, which is the study of how we know things about the world. That when you get to, so first let's take our mesoscopic world that we're familiar with. As you walk around and talk to your friends and go to class, you never see identical things, right? If you see a field of cows, you're like, oh yeah, there's a bunch of cows. But if you look at them more closely, you see, oh, the cows are actually all different from each other. If I see you guys from far away, I'll say, okay, there's just a crowd of people. There's just a bunch of people. But if you look at you guys up close, oh, everyone has different faces. They have different memories, different thoughts. They're different people. They're distinct. There are no identical things as such in the mesoscopic world. This is in stark contrast to how we describe the microscopic world. All protons are exactly identical to all other protons. They're all the same thing. All electrons are identical to all other electrons. And the point I want to emphasize is, on the one hand, you can say, okay, maybe the universe is, like, we're getting to the smallest things. Those are fundamental. But I think that's a conceit that's not justified, because first of all, it kind of gets to the, there's this steady progression in human thought. Initially, we all thought that the Earth was the center of the universe. Everything revolved around the Earth. And then that was called the geocentric. Thank you, Lewis. Geocentric theory. And then Galileo came around and was like, oh, no, it's not. Galileo, right? Did I get that right? Copernicus, excuse me. Get these guys mixed up. Anyway, he worked out, oh, actually, no, we go around the sun. And he got all kinds of shit from the church about that. But it turned out he was right. And so, that was sort of a progression from us being the center of the universe to, oh, we're going around the sun. Similarly, I think that same type of thing applies to length scales. We would like to think that the length scale, which is on the order of a meter that we're intimately familiar with, is somehow more fundamental in that when you get smaller than that, you could reach some limit where everything is just little Lego building blocks, and then you build them up to build the world around you. And that's kind of how we like to think about things when we start thinking about physics. But it's not justified. And I think I can't really prove this, but my personal opinion is that at any length scale, the universe should be fundamentally indistinguishable from any other length scale. There shouldn't be any fundamental length scale. The universe should be infinitely complex, no matter how you look at it. But it's a really interesting thing, because physics does work, and it works by modeling protons and electrons as all being identical to each other. Another thing you can notice is if you just look outside at night, if you're outside of the city, you see all these stars. And of course, all these stars are just different and distinct. But for all you can tell, they're all just a bunch of points of light. Right? They all look kind of the same. So it's weird it works in both directions. When you look out really far, really huge distances, because of the way you're looking at it, these stars are distinct. But because of your perspective, they all look basically kind of similar. And I think the same kind of thing happens with microscopic physics. That it's an artifact of our perspective more than it is that that's actually the fundamental scale of reality. This gets into why I hate high-energy physics and particle accelerators, because they're super expensive, and they're using up all the funding, and I can't get any, and I just need a computer. But that's a whole other tangent that I'm not going to get into. Any questions so far? One third thing, which I didn't have room for on the previous slide, limitations of classical mechanics, is that there's probably no such thing as a fundamental particle. Meaning there's no logical starting point to the universe where once you work down to that, then the entire universe is a bunch of Legos, and you just build them together to just get what's around you. At any length scale, the universe should have some level of complexity and intractability. And that is our primary conundrum. That's the tricky thing. So a few, I think, plausible problems are that, so what if the universe, in the universe, all things have internal structure. No matter how small they are, there's always stuff going on inside of them. And the universe has complexity at all length scales. These are the limitations of classical mechanics, and that sort of gets to why it doesn't work symmetrically like we would like it to. So let me connect this to what we've been doing recently in class, which is, so I've argued that classical mechanics and quantum mechanics are symmetric, and that's somehow a limitation of the models. But physicists have realized this, and they have done a lot of work that incorporate this asymmetry of time. In particular, the main way to incorporate asymmetry in time is through statistical mechanics. So time asymmetry comes about with statistical physics. And that's what we were doing, whether we knew it or not, with the ideal gas law last week. So let's say we have a balloon that's filled with helium. And it has pressure P that we know because we measured it. It has volume V. And it has n moles of helium atoms in it. So we know that helium is really well approximated by an ideal gas, so it'll obey the ideal gas law very closely. So that means since PV equals nRT, and R is just a constant, we know that the temperature of this gas is also going to be just PV divided by nR. So if we know its pressure, volume, and number of moles, we know also what its temperature is. And then once we get this far, we can use physics to describe the behavior of this gas. If we do something to it, we know what's going to happen to these quantities. However, the microscopic description of what's going on inside this balloon, that's not how you spell description. So the microscopic description of the atoms is statistical in nature. And what I mean by this is that we know the pressure, volume, number of moles, and temperature, but we don't know exactly where every atom in this balloon is. And in fact, if you take a particular atom, it could be anywhere in that balloon. And if you move things around right, you would still have the same pressure, volume, and temperature, and number of moles. So there's actually an infinite number of different positions it could be in, because in any finite space, there's actually an infinite number of points, if you guys ever remember Zeno's paradox. So there's actually an infinite number of different arrangements, different ways you could arrange the atoms inside this balloon and get the exact same microscopic system. So our description of what's going on is fundamentally statistical in that we don't know and don't actually even care to know, because it wouldn't actually be useful because it's too many numbers to keep track of, what the exact microscopic description is of this balloon. This is what breaks the symmetry of time, that uncertainty, which I will explain very shortly. Everybody still writing? Anybody still writing? A few are. Give you a second. So this is what breaks the symmetry of time. How does it do that? We will see shortly. OK, say we have a new situation. We have a box, and we put a partition in the box. This is just a wall that's movable. And we fill this side of the box with a bunch of helium. So here we have n moles of gas. And this vertical line here is a partition that we can move around. So if we move this partition to the right, we all know intuitively that the gas is just going to expand to fill the whole box, right? And there'll be a lower density of molecules, so that'll in turn lower the pressure. Or if it was doing work, that could also lower the temperature. Depends on how you do it. But you're going to get this. If you know how the process goes, you can know the new macroscopic state. If you then let this thing sit around for a while, it is never in a million years ever going to spontaneously have all of the gas moving back to where it was to begin with, right? This is not going to happen. The gas is filling the whole volume. It's not going to spontaneously go back and fill half the volume. So that is fundamentally where asymmetry in time comes from, one way of looking at it, at least. And the reason for this is that on the left picture here, well, let's call these situations 1 and 2. So, and these two are the same, except there's no partition there. So for 2, there's still an infinite number of places where things could be. And there's an infinite number here. But this is a larger volume, so there's actually a bigger number of infinite possible positions of the atoms and the molecules. So what I'm saying is that the large number of positions and velocities that they could have is actually infinite. But infinity 1 is bigger than infinity 2. And that's crazy, I know. Doesn't mean it's not true, because it is. This is actually, so the infinity is actually only if you deal with this classically. Really, if you get into what's going on with the particles, when you get down to the microscopic description, you have to start using quantum mechanics to describe what they're doing. In that case, the infinity actually becomes finite, and there's a finite number of states available to the particles here, another finite number here, and this number is bigger than that one. Classically, though, if you're careful about it, you can still compare different, they're called orders of infinity. And this one is larger by some tractable amount. Anyway, point being, this number of possible ways of getting a macroscopic state is related to the entropy of the system, which you guys have probably heard of. So number of possibilities is related to the entropy, which is denoted by S. And the second law of thermodynamics, which I'll write specifically on the next slide, that in a closed system, if you're not giving it any energy or doing anything and you work on it, the entropy can only increase as time goes on, which means that as time goes on, this can spread out to be like this, but it would never spontaneously go back to like this because there's fewer ways to do that. This is probably kind of abstract, and there's a lot of infinities going on, and this may not make any sense. Anybody confused? Anybody? Oh, maybe you guys do get it. Well, I'm going to give you, for the few that are confused, I'm going to give you a little more of an intuitive explanation of this same concept. So let's say we're playing, you know that cup game where you put like a pea under a cup, and some guy in like a flea market, you know, with a weird accent is telling you that He's going to mix them up, and then you have to guess where the P is. You know what I'm talking about? So we're going to label these cups. We have 6 cups. And he's going to like shake them around, and you have to figure out where the P is at the end of the day. So initially, say you know, because either he told you or say for whatever other reason, you know the P is in either 1, 3, or 4. You don't know which ones. Which one exactly? You know it's in one of those 3. So this guy does this thing where he moves all the cups around, and he's really fast because he's been doing this for a while, and it's hard to see what he's doing. But you do your best to try to keep track of all the cups, and you get into some final configuration where he puts them back down. Now he asks you, okay, where's the P? So at the very, very best, the best you could possibly do is keep super good track of what's going on and say, okay, after he's done, I still know where 1, 3, and 4 are, and I still know it's one of those 3. More likely, if he's doing what he's doing pretty well, you weren't able to follow exactly, and so maybe now you only know it's in one of these 4 rather than one of these 3. Like your knowledge of what's going on could have gotten a little bit worse, but the important point is that it could not possibly have gotten any better. There's no way for after he does all this stuff, or suddenly you didn't know, oh, it's actually definitely in the left one. There's no way for that to happen, right? Because you didn't know beforehand. So your uncertainty in what's going on in the situation can do nothing but increase. If you're really careful, you can keep it the same, but it's not going to get any smaller. That is exactly the same as the second law of thermodynamics. Second law of thermodynamics says you don't know exactly where all these molecules are. So as time goes on, as they evolve and do their thing, you're not going to suddenly know what the number of possible microscopic positions is not going to decrease as time goes on if you just leave it to its own devices. The reason is that there's fewer possibilities here than here. So if you just let this thing evolve naturally, that can only increase as the uncertainty and the random motion kind of propagates out. It will never decrease. So in a nutshell, time is asymmetric because our starting knowledge is statistical. We know that it's in one of a number of different possibilities. You don't know exactly what's going on. And that number of possibilities can only increase or stay the same in any isolated system. Isolated is an important word here, because if you have a partition and you squeeze this gas back over to the right or to the left, then you can change the entropy and make it decrease. But you have to put energy onto it. That's also why the creationist argument about the second law of thermodynamics disproving evolution is completely ridiculous, because there's the sun, and the sun gives us lots of energy. So entropy doesn't have to strictly increase on the Earth. Any questions about this? Okay. So let's make this a little bit more quantitative. The definition of entropy is the same Boltzmann's constant that we had in the ideal gas law times the natural log of W, where W is the number of possible states. So if you have a gas in the balloon, there's a number of possibilities of where all the molecules could be. As that balloon gets bigger, that number increases. So classically, W is infinite, but quantum mechanically, it's actually finite. In either case, the entropy is related to the natural log of how many possible configurations would give you the same macroscopic situation. And since there's this starting uncertainty as the system evolves, that number of possibilities can only get bigger, just like the P's. Any questions so far? So if you have your coffee cup and you drop it on the ground and it breaks, you're going to get little pieces flying everywhere. And they're eventually going to settle on the ground, and then their energy is going to get transferred into heat in the floor, and that's going to get dissipated, you will never see all that heat coherently come back into the coffee cup pieces, give them just enough energy to make them fly off of the ground and run into each other in just the right velocities to make the atoms rebond into a solid coffee cup, along with all the water that goes back into it, and then it all hops back up into your hand. That won't happen. The funny thing is that if you take classical mechanics too seriously, you'd say, oh, well, yeah, it probably won't, but there's actually a finite possibility of it. And that is a dangerous, dangerous thing to do. I encourage you not mistake the map for the territory. Because that actually, if you take classical mechanics at face value and say, okay, then you actually could have a specific arrangement of all the atoms in the floor that coherently transfer the energy back into the cup and make that happen. That is possible according to the theory. It's not possible according to reality, and that's an important distinction to make, that is a limitation on the theory. It doesn't actually do that, even though if you look at it, you can work out the probability of that happening, and it would only happen once, like 100 times the universe goes on, probabilistically speaking. But anyway, I think it's pretty safe to say that the probability is 0. You can round that down, because it won't ever happen. OK, so the second law of thermodynamics is that the change in the entropy of a system is always greater than or equal to 0 for any isolated system. The only way to decrease the entropy, which is the number, so I'm sorry, let me have a bit of a tangent. So in common parlance, entropy is often referred to as disorder, that type of thing. If you think about this coffee cup breaking, there's a lot of different ways it could break, where there's only one way for it to be a solid coffee cup. When it breaks, it could break along a bunch of different lines. It could be in a bunch of different places. There's more possibilities for it to be broken. Hence, it's a more disordered state and a higher entropy state. So this disorder will only increase as time goes on for any isolated system, unless if it's not isolated, that means you're doing work to it. You're putting energy into it. In that case, you can drive it back the other way. You can get a bunch of glue and glue the thing back together or something like that. You guys are really quiet. Does this make sense? OK. I thought it was pretty interesting stuff. All right, now we're going to talk about Maxwell's demon, which is a really cool thought experiment that this guy Maxwell thought of. He's the guy that came up with the unification of electricity and magnetism, which you guys will learn about in 208. So say we have this same gas with a partition in it, but now there's gas on both sides of the partition. And it's the same gas, and it's at the same temperature. So on either side of this partition, there's a bunch of gas molecules that are randomly flying around in all different directions. Because it's just an ideal gas, there's a distribution of velocities, which I think we might have skipped that section. But for a gas at a certain temperature, there's randomly a bunch of different temperatures and same temperature, a bunch of different velocities of all the different particles. Maxwell proposed this thought experiment that what if you had a tiny demon who is hanging out next to the gas. See if I can draw a demon. Here he is. He's really small, and he has this little door that you can reach over to. And this door, he can just open and shut this door, and it's a massless door. It's really tiny. And he's also has really, really good eyesight, and he's watching all of these molecules in the gas. And what he's going to do is he's going to wait and watch it. And if he ever sees a molecule flying towards this door that's a little bit higher energy than average, a little bit higher velocity than the average velocity of all the gas, then he's going to open the door, let the particle fly through, and get to the other side and close it again. If he ever sees a particle going this way that has a smaller than average velocity, he's going to do the same thing and let it go over to the right. And the point here is that he's not actually doing any work on the gas. He's just opening and closing a massless door, watching all these things. And if he does this for a while, what he can do is he can separate out and isolate the hotter ones over here and the colder ones over here. So you can have two different temperatures. So T1 will be bigger than T2. He's letting the faster ones get over to the left, the colder ones to the right. This is a lower entropy state than the initial state. This is called a paradox, apparent paradox, because this seems to violate the second law of thermodynamics. Because he's not actually doing work on the gas, but he's still separating out hotter and colder atoms, which is a lower entropy state. We talked about changing the volume, changing the entropy. having two separate temperatures is also a lower entropy condition. So this gas would never spontaneously separate its temperature out where you have hotter and colder. Anyway, this is just a cool thought experiment, good to, interesting to think about. So in this case, of course, T1 equals T2. The solution to the paradox is actually, does anyone know actually? Have any ideas what the solution to the paradox is? The solution to the paradox is that the act of the daemon looking at and gaining information about the velocities of the particles requires some tiny amount of energy to do that, to gain the information about where the particles are going. That amount of energy that's required to gain the information of where the things are is just enough to preserve the second law of thermodynamics and make everything work out beautifully. But fun to think about anyway. So information we like to think of as just an abstract quantity. It actually, if you get down to the nitty-gritty of how you'd actually be able to measure where the velocities are, you have to use some type of light or something to measure the velocity. And that tiny bit of information, tiny bit of energy required to gain this information is enough to counterbalance the decrease in the entropy. Any questions? All right, let me show you guys this demo real quick because it's cool. So this is a tank of glycerin, and I have 3 different syringes of different colored fluid. I'm not sure what type of fluid it is. It might be glycerin with food coloring. What I'm going to do is leave a streak of this stuff like this around here. So the reason we're using glycerin is that it's pretty thick and it won't just mix up too much too easily. All right, so we got a couple blue ones, a couple green ones, a couple red ones. So this is in a state with a certain amount of entropy. The entropy is lower than it would be if all of this stuff was just mixed up together. And as I crank this guy, I'll do it fairly slowly. You see, you mix all this up, and this is a much higher entropy state. Everything's mixed up. Now, if this thing works, when I turn it back the other way, because it's glycerin, it has some viscosity to it. It actually perfectly unmixes to get back to the lower entropy state. Pretty cool, right? This wouldn't work if it was a fluid. If it was a fluid with less viscosity. It's because glycerin is super thick that you're able to get back to your coherent beginnings. Anyway, pretty cool, right? You guys feel free to come down and play with it whenever we're done with lecture. OK, one more thing I want to talk to you all about. And that is the relationship between entropy and information, which also gets into cosmological questions, the fate of the universe, that kind of stuff. So let's say we have a cup of coffee, or just a cup to start with. In the bottom of the cup, we very carefully, at the bottom of the cup, we pour a little layer of cream. And above this, we very carefully pour a cup of coffee. We pour it very carefully so cream is actually slightly more dense than coffee. And we pour the coffee on top very slowly so that it doesn't mix with the cream. It's less dense and it just floats on top. This is a low entropy state as far as the mixture of the cream and the coffee goes because they're separated. And so there's not as many possible locations of the molecules when they're separated as there are if they're both mixed throughout the entire volume. If they're both mixed throughout the entire volume, there's more possible locations of them, which is higher entropy. So then you stir your coffee. As you stir it, of course, we all know eventually you'll just get a brown, uniform, homogeneous bit of coffee, cup of coffee. But I'm going to talk about the process that gets you there. So when you start to mix it, you're going to get all these beautiful swirls, which I love watching, where the cream starts to swirl in with the coffee, and things start to mix, and it's very pretty. And that's my favorite part about drinking a cup of coffee. So this is while it's mixing. After this goes on for a little while, then eventually you'll have a uniform, homogeneous, brown mixture of coffee. So we have 3 things here. We have S1, S2, and S3. These are the entropies of these 3 different states. We know that S1 is going to be less than S2, and S2 is going to be less than S3, right? As this process goes on, entropy is continually increasing as you mix it. However, if you think about this thing from an information perspective, it's very different. The left-hand side is, informationally speaking, very simple. And there's a variety of ways to quantify information. I'm going to use the way that your computer compresses images into JPEG files versus bitmaps. You guys know about BMP versus JPEGs? I'll explain it real quick. So a BMP file, image file, if you were to take a picture of this, if this was glass, you could see it, and you were going to take a picture of it, a BMP file would be a file that designates every pixel of the image and tells you what color is at that pixel. And they're huge because that's a lot of information. There's a lot of pixels to take care of. This stands for bitmap, I believe. So it'd be, so the file, if you broke down what it looked like, it'd be something like the point 00 is black. The point 01 is black. The point ... 05 million equals whatever. There's a whole bunch of, it's a big file because there's a whole lot of data points. A JPEG, there's a variety of different compression techniques. I don't actually know how JPEGs specifically work. But the general idea is it could say something like, OK, the pixels from row 0, column 0 up to row 100, column 200. So if you designate this as 0 and this is down at, say, 100 pixels and this is down at 110 pixels, and this is, say, 100 pixels across, you could say all the pixels from 0 to 100 are black, all the pixels from 100 to 110 in Y, and 0 to 100 in X are white. And that could be your JPEG file. And that takes way less words to say that, just like it takes way less memory in your image file. That's why JPEGs are smaller, because they compress it in some way to give you a smaller file. So that's a way, since this is very easily compressible, that's a way of saying that there's not much information in this image. That's contrasted to this case, where even if you try to compress it in a JPEG file, it's going to be a little bit harder to compress this into a smaller file, because you can't just say, how are you going to exactly quantify the shapes of these swirls and what color it is in what place? You can do it. You can still make it smaller than a bitmap, but it won't be as small as the left picture. This case, over here on the right, is also very simple, because if this thing mixes homogeneously, it's just all brown. So it's even easier to say what this is than this. You just say all the pixels are brown. That takes very little information to say that. So the point here is that even though the entropy is constantly increasing, the amount of information and the complexity in what's going on is not monotonic. At first, it starts off with very little information. As all the swirls come about, you have a whole bunch of information. Information increases. And then as it mixes uniformly, you go back to very low information. Anyway, it's a really interesting distinction, I think. And it's related to cosmology because the universe happens to work exactly the same way. In the very early universe, the universe's volume was very small. Everything was in a confined space. And so there's a much lower entropy. As things expanded, the entropy increased. And you get eventually all this beautiful, complex stuff that we see around us, people and trees and things. In the far distant future, when the universe continues to expand, eventually all the stars will burn out, everything will entirely mix uniformly, and you'll just have nothing but spread out, uniform, dead, lifeless dust. That's what you have to look forward to in about 10 billion years. But the point being, it's, again, low information. So information is not something that always increases, or if you can really say anything about it, that it happens uniformly. But what you can say is that as entropy is increasing, the process of entropy increasing in a system is what leads to complexity, which leads to information. Any questions about that? Great. Well, thanks, guys, for a great semester. I'll see you on Thursday for exam review. Feel free to hang out and play with the tank if you want. It's kind of fun.